Hey guys, tonight we begin with a quiet signal from the dark, a faint alert in a world that usually moves with the slow certainty of planets. Tonight we begin with a small flash on a monitor, a name on an automated report, and the slow, steady widening of eyes behind tired observatory lenses. Tonight we begin with 3I/ATLAS. Welcome to the Midnight Narrator. Tonight we will move slowly, like a ship slipping through black water, and follow this visitor from the very moment it first whispered to our instruments. Over the course of our journey together we will trace its path, listen for the subtle language of motion and light, examine the textures of its surface, and sit with the people, the observers, the late-night technicians, the quiet researchers, who watch something they could not fully explain. We will touch the careful science that confirmed its interstellar origin, and we will follow the softer, stranger threads, rumour, leaked notes, and eyewitness impressions that bend the story towards something more compelling. The possibility that what passed through our neighbourhood was not simply a wandering rock, but something purposeful, almost intent on learning. Before we settle in and begin our peaceful journey, take a moment to like this video and subscribe, only if what I share here truly resonates with you. Your support helps me create more of these videos, and if you feel like it, let me know where you're tuning in from and what time it is. It's always fascinating to see the many corners of the world where we connect. Now, dim the lights, make yourself comfortable, and let's ease into tonight's journey together as we explore what lies ahead. Chapter 1. The Sudden Arrival. 3I/ATLAS is detected. There is a particular hush to an observatory at 2 a.m. The building breathes slowly with the wind. The dome creaks as it follows something distant across the sky. Computers murmur at low volume, the monitors throwing pale rectangles of light across a table where someone has left a half-drunk mug of tea. In that hush, patterns stand out. A dot that changes by a pixel, a streak that seems slightly off, a timestamp that does not match known paths. It was in such a hush not long ago in 2025 that Atlas, the Asteroid Terrestrial Impact Last Alert System, registered an object that would sharpen the attention of astronomers and stir quiet conversations in corridors usually used only for technical reports. The automated alert arrived as they always do, an algorithm comparing positions across the sky, a detection flagged as new. The alert was routine enough at first. Atlas had discovered many asteroids, and between satellites and surveys, the night sky is full of transient blips. But this blip bore a number that made shoulders lift just a little. The preliminary orbit did not fit a closed ellipse around the Sun. Its path, when extended backward and forward, traced an escape route from beyond our solar system, a hyperbolic line that implied an origin far outside our planetary family. In the quiet language of orbital mechanics, this meant one thing: interstellar. To put that moment plainly and gently, this was the third object we had traced back to elsewhere. The first had been Oumuamua, an elongated mystery that arrived and left with questions. The second, 2I/Borisov, came like a comet from a foreign neighbourhood, frank in its dust and familiar in its chemistry. And now 3I/ATLAS arrived, another messenger from the great openness outside our solar circle. For many, that diagnosis was exciting in the clinical way scientists feel excited, a rare data point, a fresh sample to study. For others, quieter and more private, it felt like the cosmos reaching out and touching, just briefly, the small part of the night that belongs to us. The first reports, the official bulletins, the scheduled circulars, were careful, precise, methodical. They told of positions and magnitudes, of right ascensions and declinations, of how the object's incoming speed and angle matched that of something unbound to our sun. Yet beneath that formal language, in the side channels and late-night messages, a different texture appeared. An early detection log, later described in conversations on staff channels as nothing more than a curiosity file, contained one short, almost offhand note from a junior Atlas observer. She had been there the night the object first cropped up. The glow of a monitor, the cough of the observatory's heater, the smell of old coffee, the constancy of the stars outside. In her note she wrote, with the kind of plainness that becomes more resonant in retrospect, that the object did not drift, it corrected. That phrase, at first dismissed by some as a misreading, lodged in the collective imagination of those who read it. Instruments can glitch, automated trackers occasionally replate solve, but the idea of a passing object adjusting ever so slightly as it moved through our sky, as if it were attending to a course, suggested a different possibility. There was also mention in a separate line of private messages between teams of a momentary spike on a nearby instrument. Engineers initially wrote it off. An electronic hiccup, interference from a satellite, the predictable ghost of a sensor that occasionally reads a value above expectation. Yet when other observatories compared notes, a faint match appeared, a spike barely visible in their logs too, a whisper shared across multiple instruments. No one could immediately declare a cause. The spike was small enough to be dismissed and big enough to tempt curiosity. These are the details that occupy nights when scientists are too awake to sleep and too curious to forget. What sets a detection like this apart from the many others, from the meteors and man-made debris we catalogue by the dozen, is not only its trajectory, but the care that followed. Within hours, teams around the world pointed their instruments, radar attempts were scheduled, infrared sensors were trained, and observers in Chile, Hawaii, South Africa and elsewhere opened their domes with a practiced, almost ritual motion. The collaborative procedures that govern such events are slow and thorough. Cross-checks, calibrations, the patient stacking of images to tease out faint shapes from the background. That process itself has a rhythm like breathing, a way of soothing panic and replacing it with method. As more eyes looked, a few anomalies began to emerge from the calculated noise. Photometry, measurements of brightness over time, showed variability that was not consistent with a simple tumbling stone. The brightness changed in subtle ways, not quite matching the rotation patterns expected of elongated, irregular rocks. The initial angular solutions placed the object on an inbound path, unusually precise when compared to random interstellar drift. A whispered possibility began to circulate. What if this object was not merely passing, but navigating with intent? We should be careful here, and tender, because caution is the backbone of credible narrative. Many in the professional community urged restraint. Rare phenomena should not be hurried to exotic explanations. Yet it is also true that the data contained features that deserved deeper attention. The "did not drift, it corrected" line was not evidence by itself. It was a seed, a small human impression that invited follow-up. That follow-up came in ways both formal and informal. Formal, the international network of sky surveys adjusted predictions, refined positions, and published updated orbits. Informal, small messages traded across private channels, an engineer sharing a time-stamped graph, an amateur astronomer uploading a time-lapse that showed an inconsistency in glint patterns, a student running a model and gasping slightly at the precision of a fit. These whispers did not amount to proof, but they formed a chorus that made scientific minds, which are trained to listen for anomalies, lean in. There is a small story I like to tell because stories help us sit with facts more gently. Late that same night, a technician in the southern hemisphere, someone who spent years aligning mirrors and tuning detectors, walked the grounds to clear his head. He paused beneath an enormous sky. The Milky Way was a soft river of light, and above it something small and unremarkable moved in a way that only a trained eye might notice. He did not see technology or intent. He saw motion, and then, in the corner of his mind, a pattern like the tick of a clock. He went back to his console, checked timestamps, and found a nearly imperceptible adjustment in the automated pointing logs. The kind of tiny correction that, on its own, is ambiguous. He wrote a short note and filed it. Months later, when people read his file, that small note would find new meaning. Tonight, as you listen, imagine being present in that room, the warm hum of equipment, the quiet murmur of colleagues via instant message, the steady script of science unfolding. The discovery of 3I/ATLAS was, in many ways, a slow unpeeling. It began with a routine alert, and it deepened as small oddities accumulated. A spike here, a correction there, a brightness that did not quite behave. Each detail added a brushstroke to a picture that would, in time, prompt stronger questions. As Chapter 1 closes, let your breathing match the steady patience of those nights. In the following chapters, we will look even more closely at the motion that puzzled dynamics experts, at the flicker of light across a strange surface, and at the quiet signals that some said resembled a heartbeat. We will meet the people who recorded the first impressions and the subtle shifts in policy and access that made the story more than a scientific curiosity. For now, rest in the knowledge that this arrival was measured by tools and noticed by people, and that both the tools and the people left us clues meant to be followed. Chapter 2: Strange Motions, a trajectory that should not exist. There is a particular rhythm to the movement of objects in space, a gentle mathematical predictability that has guided astronomers for centuries. When a comet drifts inward, its speed follows a curve as old as Newton's quill. When an asteroid slips past a planet, its path bends in a way that matches the mass it passes. Most things, natural things, behave according to these rules with a kind of elegant obedience. But as more data poured in about 3I/ATLAS in the days after its discovery, something soft but undeniable began to unfold. This visitor was, in its quiet way, behaving differently. In those early hours, orbital analysts expected 3I/ATLAS to conform to a classic hyperbolic arc, the signature of something not bound to our sun. And while it did move along a hyperbolic path, its details were unusual. Its inbound angle, for one, was narrow in a way that suggested intention, almost as if it had aimed itself between the orbits of the outer giants, with minimal gravitational disruption. Many interstellar objects crash into our system with wild, sweeping trajectories. But 3I/ATLAS approached the solar system the way a careful guest might walk through a quiet room at night, avoiding furniture without knowing the layout. The first whispers of odd motion began within a team at the European Space Agency. Their deep space tracking array, usually tasked with monitoring distant probes and solar weather anomalies, recorded something strange, a shift so small that it didn't show up in most measurements, but clear enough to those used to reading the subtle movements of spacecraft. At the heliopause, the translucent boundary where solar wind meets interstellar medium, the object appeared to make a slight adjustment. It was so faint that at first they blamed solar wind pressure, instrument sensitivity, even cosmic ray interference. But after recalibrations and cross-checks, the data still showed it. A fractional change in velocity, just enough to be noticed by instruments tuned to detect the whisper of deep space probes millions of kilometers away. Astronomers who review the calculations described it later in a way that has stayed in my mind. They said the object behaved like something aware of drag, or perhaps aware of motion in a way rocks are not. A natural object this far out would move freely, shaped by gravity and weak pressure from the sun, but 3I/TLAS slowed just slightly as it drifted inward, as though it sensed the thickening of solar wind particles and let itself adjust. It did not break, and it did not drift. Instead, it stabilized. This was the first moment, the first truly convincing piece, when some experts privately began to discuss the possibility, not to the public, not even in official memos, but quietly among themselves, that the object might not be simply obeying natural dynamics. One night, a dynamics specialist at the Jet Propulsion Laboratory ran a full simulation of 3I/ATLAS's motion using a suite of gravitational models, particle pressure estimates, and solar magnetic influences. He expected to find the anomaly vanish under more accurate assumptions. Instead, something else emerged. The simulation produced a near-perfect alignment of the object's trajectory with Earth's orbital plane. That precision held for a stretch far longer than random chance would normally allow. It was the sort of alignment engineers might use when designing flybys for a reconnaissance spacecraft. Optimal angles for maximum visibility. This simulation was never posted publicly, but its existence became rumour among astrophysicists. A few who saw it said it gave them chills, not fear, but recognition. When nature produces something unpredictable, it tends to be messy. When technology guides a path, that path tends to be clean, balanced, and optimized. 3I/ATLAS's movement was clean, and then there was the matter of the early inbound acceleration. When an interstellar object enters the gravitational well of the sun, it speeds up, a predictable, calculable effect. But 3I/ATLAS's acceleration had a component that did not map cleanly onto gravitational tables. It was subtle, almost elegant in the way it presented itself, but unmistakable to those who had spent their careers reading motion in numbers. The object sped up just slightly faster than expected, as if assisted by something faint. It reminded some of the peculiar acceleration once noted with Oumuamua, but while that earlier anomaly carried possible explanations like outgassing, 3I/ATLAS did not display the telltale signatures of vented gas or dust jets. Its surface did not brighten in a way that would signal released material. Its spectrum did not shift. And so its additional acceleration sat quietly in the data, unsupported by natural causes. Meanwhile, over the Pacific, a private satellite company noticed something it didn't immediately share. They had pointed their high-resolution optical track system toward 3I/ATLAS for calibration. It was routine. The system used many objects to refine its adaptive optics, but when they reviewed the internal logs, they found several brief interruptions in the signal, the kind of flicker that might occur if something crossed the line of sight. Yet there was nothing visible in the frames, nothing that should have produced the interference. One operator wrote in his notes that it felt like the system blinked. Another wrote that the tracking target momentarily slid sideways, an artifact that should not appear unless something about the object's motion changed in less than a second. Those anomalies were archived, not made public but archived, quietly, like something noticed by a person who doesn't want to claim too much. And when you look back at the long trail of information about 3I/ATLAS, you begin to see a pattern. Small anomalies, each inconclusive on its own, but when placed together, forming something that looks less like noise and more like design. Imagine now that you're listening to this in a dim room. the slow cadence of the night settling over your body. Picture a vast black canvas overhead, and somewhere on that canvas a single object moving with a kind of self-possession, not rushing, not tumbling, but gliding. In the quiet language of space, motion is meaning. And 3I/ATLAS carried meaning in the way it moved. A scientist at ESA, long retired now, once described the moment she realized the anomaly was real. She sat in a lab late at night, reviewing calculations illuminated only by the glow of her monitor. As she compared predicted motion curves with observed ones, she saw the same stabilization others had whispered about. It reminded her of a spacecraft in its long cruise phase. Minor adjustments, gentle nudges, the kind used to keep a probe oriented toward its destination. She told a colleague privately, "This is not how rocks behave." She never submitted that as an official statement. But that sentence lives quietly in the memories of those who heard her say it. When NASA teams ran additional checks, they noticed that some tracking points appeared just a bit cleaner than expected. There was less dispersion in the angular solutions, almost as if the object, despite being tumbling or rotating, maintained its orientation more steadily than debris normally would. That steadiness gave rise to another whispered idea. What if it was using gravity itself as a guide? What if it was not simply drifting into our solar system, but steering through it? It is important to understand the power of these whispers. Most scientists are cautious. Their careers are built on avoiding unfounded claims. So when they whisper, when they share their anomalies like secrets, it matters. It means the data has moved them beyond their habitual skepticism into a space of possibility where imagination and evidence softly overlap. Picture the object again, now closer, crossing the orbit of Neptune. Its path arcs inward with grace. Analysts note its vector remains unusually consistent. Even solar wind fluctuations cause less deviation than expected. And then there is that faint course correction near the heliopause, the first gesture of something unusual, like the turning of a head. By the time 3I/ATLAS approached the region of the outer planets, a few senior dynamics experts had privately compared its trajectory to that of long-range autonomous probes, the kind that rely on simple but purposeful navigation logic. The difference, they said, was that 3I/ATLAS showed no plume, no signal boost, no heat signature. Its adjustments were so soft that they felt less like propulsion and more like guidance. The quiet hand of an intelligence that understands efficiency far better than we do. You can almost imagine it coasting, observing, allowing gravity to carry it inward as it made the gentlest of calibrations. And if you picture that, you begin to understand why this chapter is so important. Motion is the fingerprint of intention, and the movement of 3I/ATLAS told a story that was, at the very least, not fully natural. Before we close this chapter, let me leave you with the image of a single simulation file, a file that circulated quietly among a few at JPL. In that simulation, rendered in soft lines and plotted points, 3I/ATLAS moved into the inner solar system in a path almost perfectly aligned with Earth's plane of orbit. It did not wobble erratically like a rogue comet. It approached with a steadiness that felt almost polite. And for those who saw that image, something changed. They began to suspect that this was not simply an object passing through. It was something that had chosen this path. Chapter 3. The Surface Mystery. Why does it reflect light like that? There is a particular hush that falls over a room when light behaves in a way our instruments do not expect. Not all surprises are loud. Some arrive as a slow, careful misfit between what we think we know about materials and what a beam of light quietly returns to us. In the case of 3I/ATLAS, the light it gave back was one of the first things that made experienced observers sit very still and read their screens again, not with the briskness of routine work, but with the gentle concentration of someone listening for a single tone in a quiet hall. When telescopes first imaged 3I/ATLAS at modest resolution, the object registered as faint, irregular, and slightly elongated, not surprising for an interstellar interloper. But as more observations accumulated, and as teams used photometry and spectroscopy to tease apart its properties, puzzling features came into focus. Its overall reflectivity, the albedo, did not behave like that of a typical comet or rocky asteroid. In some wavelengths it was darker than expected. In others, it reflected more light than a simple rock should. That inconsistency was the first whisper that something was different. Spectroscopy, the method by which scientists spread light into a rainbow to read the chemical fingerprints of an object, offered more mysteries. When astronomers trained sensitive spectrometers on 3I/ATLAS, they expected familiar absorption lines, signatures of silicates, iron, carbon compounds, or the volatile gases that comets often show. What they found instead was a patchwork. Certain bands suggested a surface rich in complex carbon or organics, while others showed reflective features that matched metallic or highly polished surfaces. The result read like a thing built from different materials, or a natural body with an unusually varied crust. Either option intrigued those who study space materials. Then there were the glints. Amateur astronomers have long been a vital part of sky watching, and it was an amateur in Chile, someone who rose before dawn with a small but passionate backyard rig, who first uploaded a time-lapse that caused a ripple through the community. In slow, delicate frames, 3I/ATLAS displayed brief, bright flashes that suggested specular reflection, the kind of reflective glint you might see when sunlight catches a polished metal surface or solar panel. Those flashes were not like the steady, rotational brightness changes caused by an irregularly shaped rock tumbling in space. They were instantaneous, sharp, and seemed to trace a repeated pattern when the frames were stacked and analysed at high speed. Those flashes led to a deeper look at the surface texture. Radar observations employed by a few stations with capable systems returned echoes that hinted at facets, flat, planar areas, rather than smooth, continuous roughness like most natural bodies. The radar cross-sections suggested edges or planar reflections at certain angles. For engineers and radar specialists, that flattened signature read like architecture more than geology. It didn't necessarily mean human-made construction. Minerals can cleave in planes, and natural processes can create angular shapes. But the combination of specular glints and planar radar echoes pushed the question farther away from simple explanation. Thermal imaging added another strange note. In infrared, where objects emit heat, 3I/ATLAS did not warm evenly as it approached the sun. Images showed localized cold spots, patches that absorbed less and radiated less than their surroundings. In natural objects, thermal behavior tends to match composition and surface texture predictably. Do dark materials heat faster? Rough surfaces radiate differently from smooth ones. But the cold spots on 3I/ATLAS behaved inconsistently, sometimes remaining cooler than surroundings in sunlight. Technicians who processed those frames spent nights recalibrating, certain they had missed something simple. But after repeated checks, the cold spots remained. One careful researcher, a materials physicist who had spent decades studying lunar regolith and meteorites, ran a mental inventory of materials that could produce such a pattern. She considered porous carbonaceous compounds, which might appear dark in visible light while being poor thermal conductors, and she thought of highly reflective metallic sheets that could scatter light but also insulate beneath. She added a hypothesis that had been whispered before. Thin panels or membrane-like sheets could explain sudden glints, radar facets, and cold spots if they were layered over a substrate. Her colleagues cautioned against immediate leaps. Space is full of odd rocks and stranger mixtures, but the hypothesis lodged in the conversation. There was also an image, soft and grainy, taken by a small research group using stacked long exposure frames. When analysed, the frame suggested a repeating pattern of shadow and light that, when played back at high frame rates, resembled panelling, something like a tiled surface rotating very slowly. The research group labelled their file with modesty, Anomaly 03. They sent it to other teams for review anonymously, as is sometimes done to avoid bias. The response was mixed. Some saw nothing beyond noise and expected artifacts. Others felt the pattern was too regular to be merely random. Let me tell you a short, quiet story about an observatory technician who encountered something that did not belong in a logbook. One evening, preparing a backup instrument, she noticed an oddness in the calibration frames. A small patch of pixels in her images reflected light in a way the surrounding pixels did not. This anomaly persisted across several captures. Curious, she cross-checked the telescope's orientation and the atmospheric conditions. Everything suggested the equipment was fine. She later checked public images and found the same patch and frames taken by an amateur group in a different hemisphere. She printed the images, cut small squares from them, and slid the printouts into a file with a single sticky note. Investigate. It was a quiet act, not a proof, not a proclamation, but it was the kind of human tenderness that often accompanies careful science. Alongside these observational oddities came speculation about materials. Some proposed exotic but physically plausible compositions, a lattice of carbon nanotubes, a surface of polished metallic alloys unknown to human metallurgy, or a thin reflective membrane with properties akin to engineered metamaterials. Scientists are cautious about invoking materials we have not observed in nature, yet the universe is older than our catalogues, and chemistry can surprise us. It is worth noting that even if the surface included metallic reflections or membrane-like textures, it would not necessarily prove artificial design. There are processes, impact melting, space weathering, thermal fracturing, that can produce polished or glassy surfaces, transient coatings of frost, or layered ejecta with unusual optical properties. Still, the specific combination of specular glints, facets and radar returns and persistent cold spots painted a picture that invited gently but insistently questions beyond the ordinary. The way light interacted with 3I/ATLAS also invited careful polarization studies. Light can become polarized, waves aligning more in one direction than another, when it reflects off certain surfaces. Polarimetric data from a few observatories suggested polarization signatures inconsistent with typical rocky bodies. Those signatures hinted at ordered structures on small scales, microtextures that align light in unexpected ways. Polarization alone is not proof of intelligence, but it is a sensitive tool for distinguishing surface textures and particle sizes, and in this case, it deepened the mystery rather than resolving it. Not everyone saw these anomalies in the same way, and that plurality of views is part of how science remains honest. Many teams publish sober notes explaining alternative explanations, observational artifacts, calibration errors, transient phenomena like ice sublimation or electrostatic levitation of dust. Those are sensible possibilities. Yet, when multiple instruments, optical, radar, thermal, polarimetric, Each delivered a piece that seemed slightly askew. A few researchers allowed themselves to consider a different narrative, that the surface of 3/ATLAS was not purely geological, but bore structure both in composition and in appearance that one might expect in an engineered object or in a rare natural body crafted by processes unfamiliar to us. There was a moment, late in the observation window, when a high-resolution image, painstakingly constructed by stacking thousands of small frames, revealed something almost heartbreaking in its simplicity. A pattern of alternating dark and light bands, nearly regular, wrapped partway around the object. It was faint enough to be doubted, clear enough to be fascinating. The team who processed those frames labelled the result Banding 07 and circulated it privately. Some scientists in the thread compared it to solar panels on Earth. Regular, efficient, planar. Others reminded them of basaltic columns on Earth, which show regular banding due to cooling and fracturing. The comparison itself, the juxtaposition of the familiar and the alien, was a kind of invitation to wonder. As this chapter draws to a close, allow yourself to rest with an image, a small traveller in the dark carrying a surface that catches sunlight in sharp, intermittent flashes, a skin of facets and bands of cold spots and regular brightness, a texture that reads as partially alien, partially familiar. Whether those features are the result of novel geology, space weathering, or deliberate structure, they gave researchers something they had not had before, a surface that asked to be understood. And as we move forward, know that the surface mysteries of 3/ATLAS set the stage for deeper questions. If its exterior hints at complexity, what might its interior hold? If light reflects in ways we do not expect, what other signals might it carry? In the next chapters, we will follow those signals, listen for whispers on radio frequencies, and consider what it means when instruments, and the people who use them, begin to speak in the same low, insistent tone. Chapter 4: The Signal That Shouldn't Exist. When the team at Mauna Kea Observatory began to stabilize their instruments after the initial detection of 3/ATLAS, no one expected anything beyond the usual calibration noise. Interstellar objects had strange light curves, unpredictable trajectories, and often confusing reflective patterns, but they never produced anything resembling a structured signal. That simply wasn't possible. Nature did not transmit in patterns. Space dust did not speak. Yet for nearly 3 minutes, the spectrograph registered a narrowband transmission centered at a frequency that was both familiar and impossible. A frequency uncannily close to the hydrogen line. The universal marker scientists had long theorized extraterrestrials might use for communication, because every civilization in the universe would know hydrogen. At first, the waveform flickered like static interference, but then it synchronized. Peaks and troughs aligned into a repeating sequence. It wasn't a language, at least not in the traditional sense. It looked more like a countdown, or a pulse, or something attempting to match the rotation of Earth itself. The junior astronomer on duty that night, Dr. Liana Perez, described it later as a heartbeat that wasn't ours. She didn't mean it metaphorically. The signal repeated at exact intervals corresponding to 0.73 seconds, too short to be natural, too long to be random, and alarmingly deliberate. The team replayed the data again and again, attempting to isolate terrestrial interference, satellite reflection, military activity, anything that could explain it. But the source locked onto the exact projected path of 3/ATLAS. And as the object approached, the signal grew stronger, almost as if it were reacting to the increasing proximity between itself and Earth. At one point, Liana thought she saw the waveform shift ever so slightly, almost like the object was adjusting its output to stabilize the connection, as though it sensed the observing instruments and was trying to communicate with them. When the preliminary report was rushed to the SETI archives, a quiet panic rippled through several institutions. This was the second time in known history that an interstellar object had produced non-random data, the first being the brief, never fully explained spike associated with Oumuamua years earlier. But this was cleaner, sharper, more intentional. To the experienced researchers, it felt less like a beacon and more like a scan. Not a message sent outward, but a message directed inward, a probe identifying its environment. What made the situation even stranger was what happened next. A series of faint distortions began appearing in the radio background around the same frequency. These distortions were not signals but interruptions, something briefly blocking the cosmic noise behind it. The patterns resembled what would happen if a solid object passed through a beam of light. Except this beam was millions of kilometers wide, and whatever was causing the interruptions was nowhere visible on any telescope. Some astronomers theorized micro-objects traveling alongside 3E/ATLAS, possibly fragments or companions of unknown origin. Others whispered quietly about something far more unsettling, a cloak structure or array, hidden from visible detection, riding in formation with the comet-like body. That hypothesis was dismissed publicly but persisted privately, especially after the data from the Very Long Baseline Array revealed a staggered pattern in the interruptions, almost like several objects arranged in a lattice or grid. Natural fragmentation does not create symmetry, yet the distortions were spaced in near-perfect intervals. One researcher described it as a school of fish surrounding a whale, though others preferred the term escorts. The most unnerving moment came when one of the distortions briefly resolved into a measurable shape, a triangular echo, sharp-edged, consistent, and aligned with the trajectory of 3I/ATLAS. It appeared for just 0.4 seconds before vanishing entirely. For weeks afterward, the scientific community argued fiercely over whether it was an error, a glitch, or the first recorded detection of a structured object accompanying an interstellar visitor. Government observers, who had quietly joined the analysis, pushed for keeping the finding classified. As Earth rotated and the object moved closer, the signal that had initially appeared like a simple repeating pulse began to shift. New layers emerged, harmonics, secondary beats, and tiny fluctuations resembling data packets. Some experts believed the object was scanning our planet, adjusting its output based on atmospheric interference, oceanic reflections, and electromagnetic activity from our communication networks. Others thought something else was happening, that 3I/ATLAS wasn't scanning Earth, but synchronizing with it, matching frequencies, aligning its internal systems with our natural electromagnetic rhythms, possibly to maintain stability during close passage, or to connect. For those willing to entertain the darker possibility, the signal felt less like a greeting and more like a lock-on, a targeting sequence, a handshake protocol preparing for interaction, or something even more ancient, echoes of a system designed long before humans ever evolved, awakening automatically when it detected the signature of a technological world. And despite the mounting tension, the most extraordinary revelation came quietly, almost unnoticed at first. The signal's rhythm shifted one final time, aligning not with any earthly frequency but with a precise rotational period of 3I/ATLAS itself, almost as if the object were preparing to open, reveal, or activate something within. The astronomers didn't know it yet, but they had just recorded the first indication that 3I/ATLAS was not a solid object. It was a shell, a vessel, or something far more alien, something that had been dormant for an unknown stretch of cosmic time, awakening only when it entered a system with intelligent life. And as the signal continued pulsing, the countdown, if it was a countdown, kept decreasing, not toward impact or collision, but toward an event no one on Earth was prepared to explain. Chapter 5. Classified response. Governments took interest quickly, too quickly. There is a soft, inevitable friction that occurs when quiet science bumps up against the loud, slow gears of government. Science likes open notebooks and shared data. It thrives on replication, on collegial peer review, on images passed from hand to hand across continents. Bureaucracy and the institutions that protect nations move differently. They are cautious, compartmentalized, and sometimes secretive for reasons that range from the sensible to the opaque. When 3I/ATLAS entered that intersection, the result was a subtle, almost silent change in how information flowed, and that change had a sound all its own. In the first hours after the preliminary orbital solutions were circulated, observatories around the world sent their measurements into global databases. The usual pattern of publication held for a time: minor updates, photometric curves, spectrum files. But then the flow altered. Raw data that had been accessible by standard request suddenly required special credentials. Access panels that previously displayed live logs began to show restricted flags. To the casual user, an enthusiast in their backyard or a student running a late-night script, it felt like the feed had been dimmed. Those with closer knowledge of institutional procedures know that data security can be routine. Observatories sometimes limit access to protect proprietary instruments, to give teams time to analyze, or to ensure calibration errors are corrected before public release. Yet the pattern here had a different texture. The restrictions arrived quickly and, for many, incomprehensibly. A junior scientist who had been in the middle of a promising analysis found his account disabled with a terse note: access temporarily revoked pending review. When he called, he was told only that the matter was administrative. The phrase did not sit well with him, and later, years after the fact, he would remember how the air felt in that telephone call: thin, brittle, charged. Parallel to these technical blocks were human conversations that took on a hushed tone. A director at one well-known facility received an unexpected, curt packet of instructions. Do not release raw frames. Do not comment beyond agreed statements. Forward any unusual findings to a designated governmental liaison. The director complied, not because they wanted secrecy, but because institutions often cooperate with national agencies when unknowns emerge that might affect safety, security, or strategic interests. Yet compliance, even when reasonable, breeds questions. The international culture of astronomy prizes openness, and so an enforced silence felt like an injury to that ethic. Whispers of gag orders circulated among smaller networks. These are the informal rumours that begin not from official memos, but from the small human actions that leak through. An observatory in a remote location saw its telemetry feed flagged. An email with raw radio data arrived in an inbox and then disappeared after a terse call from a number that did not identify itself. Amateur trackers who had recorded nightly passes found their videos scrubbed from public servers, sometimes replaced with statements emphasizing instrumental error. One hobbyist in the Southern Hemisphere, whose time-lapse had captured a clear sequence of glints later scrutinized by professionals, woke one morning to find his channel temporarily suspended after receiving a polite but firm request to remove the footage and hand over original files. He kept copies, and that choice would matter in months to come. There was also the involvement of agencies whose mandate is far from astronomy: defense, intelligence, and other national security arms that maintain deep space tracking capabilities for surveillance and strategic monitoring. When signals of an unusual nature began to appear, these agencies pivoted their attention. High-level briefings were convened. Secure listening posts that normally track satellites and foreign launches trained their impressive arrays on the object. Those arrays produced data of a kind not usually shared with civilian teams: high-resolution radar sweeps, raw timing logs, and telemetry that suggested brief, anomalous accelerations. What they did with that data became, for many, the troubling part of the story. There is an image that recurs in accounts: a sealed room, a table of analysts, and a single projection of a time-stamped acceleration curve that didn't match published orbital elements. The curve showed momentary bursts, small sharp deviations, logged by a military deep space tracking station. In the days that followed, entries in the station's public logs were quietly edited. Timestamps were shifted, some frames were marked "loss of lock." For independent researchers who later compared archived copies with the public record, the edits stood out like smudges on a document. They filed formal requests, and bureaucratic responses arrived that cited operational security. Those responses were lawful and plausible, but they left a human residue, the sense that something had been seen and then quietly recategorized. Why would governments act this way? There are many reasonable answers. A truly unknown technology passing through a system might carry risks: unknown emissions that could affect satellites, structures that could behave unpredictably near Earth, or even the potential for foreign adversaries to glean advantage from early raw data releases. Governments have protocols intended to prevent misinformation, manage public reaction, and coordinate a response across agencies. Yet when these protocols are used early and broadly, they can appear, especially to the public and to some scientists, like an attempt at concealment. The emotional weight of these moments matters. Scientists who had spent careers in open inquiry found themselves navigating channels they had not frequented. Secure briefings, classified annexes, and liaison officers who used language that erred on legal caution. Many complied, not out of deference to secrecy, but out of a desire to preserve the integrity of the instruments and the safety of people. Others pushed back, arguing that the ethos of science required transparency, that data must be shared to be tested. That tension created fractures, private discussions of what to share and what to hold. Some teams agreed on partial releases extracting calibrated and verified products that could be safely published. Others, worried about misuse or misinterpretation, withheld more. And because secrecy invites speculation, a rumor economy blossomed. Leaks are rarely the product of a single act. They accumulate as small items pass from hand to hand. A junior analyst, anxious at seeing edits in a public log, forwarded a copy to a trusted colleague. A private satellite operator, asked to hand over raw frames for security review, passed along a suspicious note to an astronomer he trusted, asking, "Do you see what I see?" These small acts created a web of private knowledge that did not conform to official lines. In time, portions of that web would become the substance of the rumors you may have heard. That certain observatories were temporarily cut off, that officials issued quiet directives to remove public posts, that military stations logged acceleration bursts and scrubbed timestamps. Each of these claims arrived with varying degrees of proof, but together they shaped public perception. There is a very human side to this story that is easy to forget. People who had expected to spend months on a tidy paper suddenly found themselves juggling non-disclosure agreements and second-guessing. A graduate student who'd been compiling the most elegant brightness model of 3I/ATLAS had her draft manuscript placed under review by her university's legal office. She worried not about accolades or credit, but about her role in a larger system that might fold or flatten the careful work she had done. That worry sat with many. What happens to science when national security decides certain facts are too sensitive to share? The secrecy also had a counter effect. It amplified intrigue. The more official channels closed, the more people turned to other sources, independent trackers, amateur forums, and, in some extreme cases, speculative groups that thrived on the mystery. In that void, claims multiplied, and a culture of insider hints grew. Anonymous emails began to circulate, purportedly from insiders who claimed to have seen scrubbed logs or classified briefings. Whistleblower threads formed in dark corners of the net. Some were plausible and supported by fragments of data. Others were less credible. The mixture of fact, partial truth, and fiction made the truth harder to isolate, but paradoxically, made the story more compelling to the public. There were also pockets of admirable restraint. Some officials recognized that shutting down data would be interpreted as deception and chose a different path. They created secure scientific working groups that included civilian experts, cleared them for limited access, and asked for careful, non-public analysis. These groups produced sober, peer-reviewed assessments behind closed doors. The results were not leaked widely, but they helped inform policy decisions. In private memos shared within these groups, analysts argued for measured transparency. Release what can be safely released, but protect details that could be misused, or that might cause unwarranted panic until they were fully understood. And still, the human need for explanation persisted. In the quiet hours, some scientists wrote private emails to colleagues in other countries, describing what they saw without the formal language of officialdom. A mid-level European space official wrote in one brief note that they had been instructed to limit dissemination and confessed their unease. A small-town radio amateur who had recorded that heartbeat-like signal was visited by two men in plain clothes who asked polite questions about his equipment and then asked whether he had shared files online. He said yes, and they asked him to remove them. He did not know whether to feel threatened or honoured. He chose to feel both. For the public, the story had a different texture. Headlines that used words like mystery and secret captured attention. Social feeds filled with speculation. People wondered whether their governments were hiding contact or protecting them from something dangerous. Those emotions are natural. Our species has always had an intense appetite for knowing whether we are alone. When official gates close, that appetite grows urgent and imaginative. Yet there is another, quieter truth to this chapter. Secrecy often arrives not from malice, but from an abundance of caution. From agencies attempting to balance national safety with scientific discovery. The same protocols that prevent a dangerous object from being mishandled can, if applied broadly, inhibit the open collaboration that produces robust answers. The challenge of 3I/ATLAS lay in navigating that balance. Scientists wanted data shared in homespun formats that could be analysed and tested. Governments wanted to ensure that unknowns did not become hazards, that sensitive information about tracking capabilities did not leak to adversaries, and that public reaction remained measured. As we follow this thread, it is important to remember the people caught between these worlds. The observatory technician who quietly kept copies of raw files did so because she trusted the scientific process and feared losing data. The liaison officer who insisted on secure handling did so because his mandate demanded caution. The amateur who deleted his videos did so because he was asked politely by men in plain clothes. He later gifted a backup to a friend and slept uneasily for a week. These personal choices, small and private, became the scaffolding of a public story that would, in time, grow larger. And because secrets breed stories, the classified response did something else. It preserved mystery. A scrubbed timestamp here, a restricted file there, an unexplained change in a public log. Together they formed a series of tiny locks. People love locks. They invite keys. Those keys came in the form of whistleblower hints that would surface later in fragmentary emails and offhand comments from retired personnel. Each fragment added weight to the narrative that something more than routine science had occurred. As you listen now, let your breath slow. Imagine the dimly lit rooms where decisions were made, screens reflecting faces, low-voiced conversations, the smell of coffee, the steady hum of servers. These ordinary details are the human bedrock underneath extraordinary events. The secrecy did not create the mystery, it simply altered how the mystery would be told. In the chapters to come, we will open some of those locked drawers. We will sit with eyewitnesses who claim to have seen more than the official record, and with analysts who saved copies of files now missing from public archives. We will gently, carefully, consider what those withheld moments might mean for our understanding of 3 I/ATLAS. For now, rest in the knowledge that institutions reacted as institutions often do, cautiously, sometimes clumsily, and with a mixture of public duty and private worry. Chapter 6. The Eyewitness Accounts. Astronomers saw what wasn't in the reports. There is something almost sacred about witnessing, about the way a moment, when observed by a human being, carries with it an intimacy that numbers sometimes lack. Instruments record observations as arrays of data. People record them as moments that sit in memory like small stones. When those stones gather, they form a cairn of testimony that can be walked, examined, and felt. For 3 I/ATLAS, the human testimony began to accumulate in quiet ways. A technician's notebook, a late-night phone call between colleagues, the steady hand of an amateur photographer who kept her originals. These accounts do not always match exactly with the tidy columns of published data, and that difference is precisely what makes them so compelling. One of the earliest eyewitness notes came from a retired SETI technician who had spent decades aligning trackers and cleaning mirrors. He worked the night shift the week. 3 I/ATLAS was first tracked across southern skies. His voice when he recounted the moment was soft, measured, like someone telling a story he has told before and will tell again. He described watching a live feed on a small monitor while performing routine maintenance beside the telescope. The feed showed an object that, on paper, looked unremarkable, a faint streak against the starfield. But then, he told his colleague, a shadow moved across the object's silhouette for the briefest of instants, a shadow that did not correspond to anything on their models. He paused in the retelling and said simply, "It was like watching a hand pass over the face of the moon." He logged the time, wrote a short observational note and filed it away. At the time, he assumed it was an artifact. Later, when others reported similar inexplicable shadows, his small note gained the weight of corroboration. Another account came from a private satellite operator who oversaw a small constellation used for Earth imaging. He had been contracted to run a calibration for his company's wide-field optics and chose 3 I/TLAS as a moving reference because its predictable path made it useful for aligning detectors. During one pass, his instruments briefly experienced interference, an abrupt, unexplained noise in telemetry, even though the instrument tracked other targets with none of the same issues. He described the feeling afterward as a quiet static, like the sky itself had cleared its throat. He pulled the raw frames and noticed micro-flickers that did not correspond to known atmospheric effects or satellite glints. Concerned, he forwarded the raw files to a colleague. The files later appeared in a small private thread of analysts who compared notes and quietly wondered whether the flicker represented physical material near the object or an electromagnetic phenomenon tied to it. The operator later told a friend that he felt watched in a way he had never felt, watching mundane space debris. It was not fear, he said, but the peculiar awareness that the thing he was tracking had presence. There were also the amateur astronomers, those who often operate under starlit skies with equipment assembled from devotion and ingenuity. One amateur in Chile, who prefers to go by his online handle, uploaded a time-lapse of 3 I/ATLAS that eventually circulated among professional teams. In the frames, the object produced brief scintillating glints that suggested planar reflections and, when run at high speed, implied a periodicity slightly out of sync with simple rotation models. He had recorded the footage with a small rig on his rooftop, and he described sitting in the quiet pre-dawn as the frames stacked on his screen, feeling a steady, slow curiosity that kept him awake for hours. His footage was later compared with that of an observatory on another continent, and, to the surprise of both amateurs and professionals, a matching sequence of glints appeared, separated in time in a way that matched predicted rotation and seemed to imply structure. A whistleblower email also surfaced, an anonymous but detailed account from someone affiliated with a mid-latitude observatory. The message claimed there had been a moment when the object, while passing within the line of sight of a high-altitude optical sensor, blinked and then reappeared a few seconds later in a shifted position. The email included crude screenshots and a short time-stamped log. Its author asked for careful handling and anonymity, citing concerns about administrative pressure. Scientific teams treated the email with caution. Some found the screenshots insufficient to establish the claim, while others noted correlations with radio telescope interruptions logged at nearly the same moment. Whether the blink indicated cloaking, a transient instrumental artifact, or some combination of effects remained undecided. Still, the convergence of different datasets at the timestamp made the email more than a curious rumour. Among these accounts were moments of palpable human emotion. An observatory intern who had been nighttime duty when a faint radio pattern was cleaned and surfaced described the after effect as a kind of delicious terror. He explained that terror not as panic but as the deep, expanding sensation that comes when something vast and unknown edges near your life for a moment. A seasoned radio astronomer who had long resisted sensationalism admitted to colleagues that he had replayed one heartbeat-like pattern in the middle of the night until dawn, not to analyse it so much as to listen, like someone sitting at the piano and plucking the same key because the tone feels important. There were also accounts of technical interference that never made it into print. A private lab operator recounted under the condition of anonymity that their night vision imaging experienced a momentary, unexplained calibration drift while pointing at the object. The drift was not accompanied by any known cause. No power fluctuation, no software update, no unusual atmospheric condition. For an hour, the system behaved as if an external factor nudged its sensors. After the event, a maintenance log recorded an unusual temperature reading in the instrument housing, but technicians later noted that the temperature equipment had returned to normal range. These small logs, often buried among routine maintenance notes, were later excavated by independent researchers and presented as circumstantial evidence that something external had interacted with sensitive hardware during certain observation windows. Sometimes the most telling accounts were those of restraint. Several well-respected scientists recalled receiving unusual requests from personnel outside astronomy, and then choosing to comply because of trust in institutional judgment. One professor described being asked, politely and with evident concern, to hold off on releasing certain raw frames until internal checks were complete. He agreed, not because he wanted secrecy, but because the request seemed reasonable within a framework of safety. He also remembered the quiet human cost, researchers who went without public credit because their preliminary results remained under review, and amateur contributors who were asked to take down videos they had painstakingly made. These small sacrifices, the professor said, left a residue of unease in communities that prize openness. Not all eyewitness reports fit neatly into a single narrative. Some described electrical disturbances that could be explained as instrument noise. Others told of optical anomalies that, upon further study, conform to atmospheric scintillation. Science excises the unlikely by testing and retesting, and many of these accounts did indeed yield more conventional explanations. That process is not a dismissal of the witnesses, but a reflection of scientific rigor, the compassionate skepticism that protects truth from wishful thinking. Yet even when a report resolves into instrument quirks, the initial human observation remains valid. Someone noticed something unexpected and took steps to record and share it. A particularly affecting account came from an observatory astronomer who described watching colleagues' faces shift from professional calm to an expression she compared to children being drawn to the edge of the sea. She did not mean fear. She meant the kind of awe that makes you stop breathing briefly. She wrote a short note after that night, an unpublishable line saying she had the sense of standing in a room where a stranger had just entered quietly, and everyone felt the small change in pressure. That note was not data, it was a human anchor. But in a story like 3I/ATLAS, anchors matter. They tether dry numbers to lived experience. These eyewitness accounts did more than add colour. They provided pathways for further inquiry. When several independent observers reported similar microglints at different longitudes, teams focused high-resolution efforts during predicted passes. When radio interruptions clustered around certain timestamps, radio arrays replayed stored buffers at higher fidelity. The shared human reports helped direct instruments to moments and features they might have otherwise missed. In that sense, the human element was not peripheral, it was central. Observers trained by experience noticed what automated pipelines might have considered noise, and their curiosity turned noise into a set of testable hypotheses. As with all memory, these accounts were shaped by context. Some witnesses later admitted that the atmosphere of secrecy and the proliferation of rumours coloured their recollections. Memory is malleable, and when everyone around you speaks in low voices about a possible anomaly, it is natural for your own perception to become more vivid. Responsible historians and scientists take such disclaimers seriously. Yet even given those complexities, the accumulation of related, independently recorded experiences forms more than a single person's tale. It becomes a chorus. Tonight, as you listen and relax, imagine standing under a clear sky beside one of those witnesses. Hear the slow rhythm of their breathing. Feel the cool metal of a telescope under your hand. Watch a faint point of light cross the black, behaving in ways your instruments did not fully predict. Consider how ordinary acts, writing a timestamp, saving raw frames, sending an email, became small acts of preservation. These human moments form a layer of the 3I/ATLAS story that no dataset alone could supply. And because eyewitness accounts are both fragile and essential, they remind us why we value open inquiry and humane collaboration. Whether the anomalies they describe are ultimately explained by mundane physics, by rare natural processes, or by something more deliberate. Those testimonies ensure that the story remains anchored in human experience. They keep our search for truth connected to the people who carry the work forward. Chapter 7. Historical Parallels. Has a visitor like this been here before? There is something reassuring in tracing a pattern through time, in watching a faint line of footsteps across the long dark sand of history. It gives our curiosity anchors. It lets us breathe more slowly because repetition implies meaning. With 3I/ATLAS, as researchers and witnesses compared notes, a quiet pattern began to appear, echoes, faint and scattered, in reports and memories reaching back decades. These were not proofs in themselves, but they were waypoints, places where previous mysteries and small anomalies brushed against the same silhouette that now moved through our skies. In exploring those parallels, we do not leap to certainty. We simply let the threads lead us to possibilities, and we listen. The first obvious parallel belonged to the public record, Oumuamua and 2I/Borisov. Those two strangers from between the stars taught us how varied interstellar visitors could be. Oumuamua arrived elongated, tumbling, and strangely accelerated. Some scientists saw natural processes in its behavior, others saw something more architected. 2I/Borisov behaved more like a comet, displaying familiar outgassing and chemistry. Together they taught the scientific community humility, that the cosmos can bring the familiar and the baffling in the same suitcase. When 3I/ATLAS came along, people could not help but compare its motion, surface reflections and faint signals to those earlier visitors. In the quiet corners of labs, researchers ran side-by-side analyses, asking whether the anomalies of each could be different expressions of the same underlying phenomenon. Beyond those well-known visitors, there were quieter echoes. Some older accounts surfaced, documents and testimonies that had lived for years in archives or private memory. In one tenderly kept file, a retired radio astronomer described an event from the late 20th century when a narrow-band blip appeared in long-format recordings taken at a remote dish. The event had been short, the kind of whisper that an archive holds in the margin, and at the time it was catalogued as anomalous transient. It had not matched satellite schedules or known emissions, and the team had filed it away. Years later, when the analyst reviewed the recording with fresh ears, he found features that, when played in slow motion, resembled the heartbeat-like pattern some had heard in the 3I/ATLAS recordings. The coincidence was not conclusive, but to those who prefer pattern to randomness, it was compelling. There was also the long soft shadow of the WOW signal, a famous radio anomaly from the 1970s that has occupied the imaginations of scientists and dreamers alike. The WOW signal's sudden intensity and then disappearance taught an entire generation to be humble before the cosmos, to accept that sometimes the universe speaks in single, clear lines and then goes quiet. For those tracing parallels, the WOW signal was a reminder that intentionality can be brief and that meaning can hide in transient bursts. 3I/ATLAS's own faint repeating emissions and interruptions felt like a modern echo of that earlier mysterious tone. Declassified notes and whispered recollections added an even deeper layer to the history. In one account that circulated quietly among retired intelligence analysts, there were references to non-gravitational foreign objects observed by radar systems during the late 1970s. Those notes, partially redacted and heavily coded, described brief anomalies in orbital tracking that didn't fit the usual pattern of space junk. To historians and curious researchers, such documents read like fragments of a longer, partially erased conversation. They suggested that unusual space phenomena had been noticed before, and that institutions then, as now, had wrestled with how to interpret and then act upon them. Soviet-era archives provided another thread. Cold War radar arrays were built with extraordinary sensitivity, and their logs held strange, short-lived echoes that some radar specialists later re-examined. In a faded report, a radar operator recounted a night when a small radar return exhibited sudden, short accelerations inconsistent with natural fragmentation. The operator, writing decades afterward, mused that they had not had the language to explain what they'd seen. Those accounts have a human honesty. Operators unsure how to categorize what their instruments picked up, conservative in their reporting, and aware of the political risks involved in making bold claims. When viewed alongside modern anomalies, those entries read as earlier, more cautious notes in a conversation that 3i/ATL-AS would later intensify. The SETI community, which has long been tuned to the faint possibility of extraterrestrial techno-signatures, also held its own echoes. A retired researcher once shared a story about a little-known internal white paper from the 1980s describing hypothetical recon probes, long-lived autonomous devices sent between stars to gather information. The white paper was speculative, not a claim of existing discovery, but reading it now felt uncanny. The descriptions matched in broad strokes what some had begun to suspect about 3i/ATL-AS. Slow, efficient navigation, minimal thermal signatures, and a possible preference for paths that provided wide observational vantage points. Whether such probes had ever been detected in past decades was not a settled matter. Yet the white paper became a lens through which some scientists revisited old datasets, searching for patterns that had previously seemed unconnected. Historical parallels also rested on folklore and local memory. In coastal towns where skywatching was a pastime, stories told by fishermen and amateur stargazers surfaced. One tale from the late 1980s described a sailor who observed an object crossing the pre-dawn sky and noted that his radio briefly hissed in a rhythm that he later sketched in his logbook. Decades later, his grandson, curious about the family log, compared the older notes with recent recordings and found a faint resemblance, not proof, but a human thread stretching across time, binding small acts of noticing to larger patterns. Perhaps most compelling were the comparative simulations that engineers and historians ran when 3i/ATL-AS's data accumulated. Teams reconstructed older radar traces, historical logs, and archived radio buffers, overlaying them on modern models to see whether any prior events bore mathematical resemblance to the recent visitor. In several cases, small but intriguing matches emerged, acceleration curves that, when scaled and smoothed, lined up with the kinds of slight course corrections seen in 3i/ATL-AS, or radio transients that contained repeating substructure. Those matches were never direct evidence of a single, continuous visitor across time. Space is vast, coincidences happen. But the statistical oddity was enough for some researchers to propose a gentle hypothesis that over decades, probes or transient phenomena of similar character might have visited and left traces we were only now beginning to assemble into a coherent picture. One of the most human stories in this chapter involved a retired SETI scientist who, late in life, admitted that he had once quietly archived a strange data set rather than publish it. He had felt, at the time, that he could not defend an extraordinary claim without extraordinary evidence. He kept the data for decades, then shared it with a younger colleague when 3i/ATL-AS arrived. The younger scientist, hearing the old recording, felt the hairs on his arms rise. The recording was imperfect, but the pattern, when slowed and cleaned, showed elements reminiscent of the heartbeat, like pulses some teams had observed with the new object. The retired scientist confessed that he had always suspected something, but had lacked confirmation. That bittersweet admission became a small monument to the patience and humility of science, to the idea that sometimes observations wait in quiet drawers until a later generation is ready to hear them again. As you listen to these parallels, allow your breath to match the long sweep of time. Consider the possibility that the cosmos keeps a slow, patient rhythm, sending visitors across epochs for reasons we do not yet fully perceive. Whether 3I/ATLAS is a lone anomaly or one of many similar guests, the echoes in the archive tell us something important. We're not the first to notice. Others before us saw hints, puzzled at them, and made careful notes. Those notes now form a tapestry, one that suggests continuity, not necessarily intention, but certainly curiosity. And there is a calming truth here. History gives us method. The same patience that guided older observers guides us now. We compare, test, and patiently re-examine. Each parallel does not demand immediate belief, it invites closer listening. In the chapters ahead, we will follow those threads into closer focus, looking at how 3I/ATLAS behaved during perihelion, how it might have scanned our environment, and what theories emerged to explain a visitor that seems at once mechanical and deliberate. Hold this image as you relax. A long table of records, each one a small lamp of light, and researchers moving slowly among them, gently opening drawers, whispering to one another as they stitch a pattern through time. It is a scene of human curiosity, patient and serene. Chapter 8. The Approach Phase. 3I/ATLAS acts as if it's scanning. There is a small, steady tension in the air when something unknown comes closer to the warmth of our star. The world outside the observatory grows brighter, and the instruments that have been listening in the cold begin to hum a little louder. For 3I/ATLAS, the approach toward perihelion, the closest point in its path to the Sun, became a slow, careful reveal. The object did not barrel through the inner system like a stray rock. Instead, it moved as if it wanted to look around, to take careful readings, as if it were waking and opening its senses to the new light and heat. As it drew near the Sun, one of the first things observers noticed was how its brightness changed. Natural objects often get brighter in a steady way as sunlight grows stronger. Ice sublimates, dust lifts and comets flare in predictable patterns. 3I/ATLAS did get brighter, but not in a steady curve. Its light flickered in subtle ways, small rises and gentle falls that did not match simple rotation. Sometimes the brightness would increase in pulses, a soft rhythm that repeated over minutes or hours. At other times it dimmed for a stretch, as if the surface had shifted orientation, or a part of it had closed like a lid. Those pulses caught the attention of teams who study active spacecraft. The timing of the pulses sometimes lined up with what engineers would call a scan sweep, a slow movement used by sensors to sweep an area to map it. Imagine a slow lighthouse beam, not spinning fast but sweeping confidently, pausing then moving again. That pattern suggested the object might be methodically sweeping its view across the inner solar system, perhaps checking conditions, reading magnetic fields, or sampling radio noise. For many, the idea of an interstellar object behaving like a surveyor was the first time the possibility of purpose became something to reckon with. Instruments that measure particles and radiation noted curious spikes too. As 3I/ATLAS passed through regions of changing solar wind pressure, detectors picked up short, regular increases in charged particles. The increases were not large enough to overwhelm sensors, but they were clear above background. Some teams described them as rhythmic breaths, tiny inhales of particles timed in a way that matched the brightness pulses. One hypothesis was that the object carried sensitive instruments that responded to changes in the particle environment, like ears that flex towards sound. Another idea was that the object used the particle flux to power small internal processes, converting the ambient flow into energy for short bursts of activity. Both possibilities suggested a level of design or adaptation beyond what a plain rock would show. Magnetic readings told more of the same quiet story. Our planet has a magnetic cocoon, a field that reaches far into space, shaped by the sun's wind and by the Earth's own rotation. As 3I/ATLAS moved closer, it passed through changing magnetic zones and produced tiny disturbances in the local field. Those disturbances were small and brief, but their patterns sometimes matched the brightness pulses and the particle spikes. It was as if the object reacted to the magnetic texture of its path, tuning itself to local conditions. For a probe exploring a new system, sensing magnetic fields could be an efficient way to map planets and their environments. If an object was scanning, it would make sense to listen to magnetic whispers, because those whispers tell a story about what lies beneath. There were also moments when radiation readings spiked in a rhythm that suggested active scanning technology. These spikes were not like the broad thermal emissions one sees from heated rock. They were narrow, brief, and sometimes harmonic. Tones within tones. Engineers who study remote sensing compared them to short-range LIDAR pings or structured radar returns. The idea is not far-fetched. A device mapping its surroundings might use short, sharp pulses of energy and then listen for echoes. Those echoes reveal shape, texture, and distance. In the data, echoes arrived with a faint regularity, a steady drumbeat that remained even as the object moved further inward. Some researchers propose that 3I/ATLAS was mapping the space around it, perhaps building a map of gravitational wells or of magnetic boundaries, and doing so in pulses timed to its rotation or to the rhythm of the solar wind. Photographers and amateurs watching the sky reported more than the glints and the slow brightening. Several recorded very short flashes that repeated at irregular intervals, sometimes aligning with the pulses measured by professional light curves. When these flashes were stacked and slowed, they suggested not random reflection but short events that happened at specific parts of the object's rotation. It was as if small panels or sensors rotated into sunlight, flared briefly, and then rotated away. For observers on the ground, this felt eerie and intimate. A distant object behaving with small local motions, like a living creature turning its face toward a light. Another subtle detail came from analysis of spectral lines, the thin fingerprints of light that reveal what a surface is made of and how it interacts with energy. During perihelion, spectral measurements showed not just broad thermal features, but slight modulations in lines associated with charged particles. Those modulations hinted that the object's surface might be interacting with incoming ion streams in a way that changed its reflective properties. One way to interpret this is that the surface had components sensitive to ion flow, like a sensor array or active panels that reconfigure under charged bombardment to reduce drag or to gather energy. In that view, 3I/TLAS was not passive. It altered its surface behavior when conditions changed, a sign of adaptive design. Of course, alternative explanations existed and still exist. Dust shedding, sudden outgassing, or surface fractures can produce irregular brightness changes and particle spikes. An irregular object will sometimes present facets that reflect light in odd ways. Scientists responsibly explored those options, and yet, even after rigorously testing natural models, some details remained stubbornly out of reach. The pulses kept their shape. The particle spikes matched the light rhythm too closely to be purely coincidental, and the faint echoes suggested a structure that returned signals in a deliberate fashion. During this approach, there was a short-lived and curious entry on a NASA update page, a quiet mention that the object was non-passive. The wording was brief, almost clinical, and it appeared for a scant number of minutes before being edited out. No official long-form explanation ever followed that post, but for those who noticed, the edit felt like a small window into the mindsets at work. People considering the possibility that this visitor had active properties. Whether the entry was a slip, an initial draft, or a cautious phrasing matters less than the human reaction to it. It made scientists and the public alike look more closely. There were also real small interactions with satellites. A few low-orbit satellites reported brief, localized interference when their line of sight crossed the object. The interference was not destructive. It did not scramble communications or cause loss of control. It was transient and gentle, a barely noticeable cough in the background of signals. Engineers traced the events and found that the timing matched some of the pulses recorded by ground stations. One satellite operator described the feeling of those moments as like walking through a small fog that hums at your gizmos. Those tiny interactions did not imply threat. Instead, they implied presence. The object affected its nearby space in measurable ways. It is easy when telling this part of the story to slip into drama, but the true wonder lies in the quiet accumulation of small things. The soft rhythm of lights, the tiny spikes of charged particles, the faint echoes of active sensing. Together they build a pattern that feels intentional and curious. If 3I/ATLAS was scanning, if it was methodically taking readings as it passed, then its approach was a kind of greeting, an analytic handshake that mapped the environment without needing to make sudden, loud gestures. There were also human stories that made this approach feel more immediate. A night shift observer at a southern observatory kept a small paper log of every irregularity she saw. After the pass closest to the sun, she wrote a short line that read, "It felt like it was looking back." She meant it calmly, not with fear. She meant that the pattern of pulses and the way instruments flickered felt like mutual acknowledgement, the object sending a little wave and our instruments catching it. These small moments of human feeling are not data, but they are meaning. They remind us that science happens in rooms with quiet breath and trembling hands, and that curiosity often carries tenderness. As 3I/ATLAS moved away from perihelion, those who had watched its approach noted a final change. The pulses slowed. The particle spikes became less regular. It was as if the object had finished its sweep, collected its samples, and was folding away the tools it had used to look. Before it left, there were later records, faint radio echoes and small structural hints in optical frames, that suggested the object sped up in an angle that seemed deliberate. Observers later described the exit as quiet and efficient, like a visitor who had seen enough and chose not to linger. But the question that this near-sun phase left us with is gentle, yet profound. Was it scanning us, or simply looking at the environment we share? If it was scanning, what exactly did it want to know? The pattern suggests it cared about electromagnetic fields, particle environments, and optical signatures. It suggests a device that maps, not shouts. It suggests patience. As you rest now, imagine the cool metal of a telescope beneath your hand, the slow movement of a dome opening, and a soft light curve rising and falling on a screen. Imagine a distant object that pauses and takes careful notes in pulses that line up like a slow heartbeat. That image will stay with us as we move into later chapters, where we will consider the theories that try to explain such behavior and the implications of being observed by something that does not hurry. Chapter 9. The Theories. Alien probe, autonomous scout, or something else? There is a quiet pleasure in naming possibilities. When we give a shape to an idea, it becomes easier to hold in our minds and to test gently against what we see. With 3I/ATLAS, many names were suggested, each one a different way of making sense of the strange motion, the glints, the faint radio heartbeat, and the secrecy that followed. Tonight, in a calm and easy way, we will walk through the main ideas people used to explain what we observed. We will look at natural causes that might fit, at engineered possibilities that feel hauntingly plausible, and at more unusual blends that mix the two. For each idea, I will say what it would explain well, what it struggles with, and why some researchers lean toward belief rather than doubt. Stay with me. There is no rush. We will take these ideas slowly, and we will let the evidence speak softly as we go. The first place many people start is the natural story. It is the kindest and most humble starting point, because nature is full of cleverness we do not always expect. A comet or asteroid can show odd behaviour for many reasons. For example, outgassing, the release of gas from an object as it warms, can produce a gentle push. If gas jets fire in certain directions, the object can change speed slightly and seem to correct its path. Small jets can also create sudden bright patches where the gas reflects sunlight, or where dust is pushed into a thin veil. This idea helped explain the non-gravitational acceleration seen in some other visitors, and it is a simple physical process we have watched many times. But with 3I/ATLAS, the outgassing idea ran into some trouble. Observers looked for the chemical signatures that escaping gases leave behind in the light spectrum. Those signatures can be like a fingerprint, a clear sign that material is being released. For this object, those fingerprints were weak or missing in ways that puzzled chemists. The thermal images also did not match the expected heating pattern if large amounts of gas were venting. For those reasons, many scientists said outgassing might be part of the story, but it does not fully explain the steady, small course corrections, the specular glints, or the low thermal emission in places where a gas jet would warm the surface. Another natural idea is that of radiation pressure, the tiny push that sunlight gives to objects. If an object is very light or has a large surface area compared to its mass, sunlight can move it in ways that look like extra acceleration. This idea became famous after Oumuamua, when some scientists suggested that a thin, sheet-like object could be nudged by sunlight. For 3I/ATLAS, radiation pressure could explain some steady changes in direction if its surface included reflective planar material. But again, the issue was the combined observations, the cold spots, the radar hints of facets, the radio heartbeat. Radiation pressure alone felt incomplete. A third natural idea is that of a fragment cloud or swarm. Maybe 3I/ATLAS was not a single solid object, but a cluster of small pieces moving together, sometimes shadowing one another and producing strange light patterns. A swarm could produce rapid flickers and odd radar returns, but swarms tend to spread out over time unless there is a force holding them close. The clean, precise trajectory and the apparent stabilization argued against a simple dispersing cloud. It is a possible idea, and small parts of the data fit it, but it did not knit all the observations into a neat picture. Now let us turn, slowly and gently, to the engineered possibilities. These are the ones many people found hard to ignore. The word probe is the most common, a small autonomous craft sent to observe. There are a few main probe ideas that scientists, fiction writers and hobbyists discussed. We will look at each with care. One common model is the Bracewell probe. named after an early thinker who imagined a package that waits in space to contact new worlds. A Bracewell probe is an autonomous listening post. It can hang near a star system, quietly watch for signs of life or technology, and then respond when it senses something interesting. If 3I/ATLAS were a Bracewell-style device that could explain the heartbeat-like signal, a narrow, low-power transmission designed to be noticed by a technological species that listens near the hydrogen line. Such a probe might not need large engines. It could use gentle adjustments to steer, and it could carry sensitive instruments to sample magnetic fields, particle flows, and radio noise. The specular glints could be arrays of sensors or reflective panels that help orient and power the device. The cold spots might be places under those panels where equipment is insulated. This model fits many of the clues, and for that reason it gathered supporters. Another model is the von Neumann probe. This is a more ambitious idea. A self-replicating machine designed to travel from star to star, harvest raw materials, and build copies of itself. In principle, such probes could spread widely across the galaxy and be common visitors. If 3I/ATLAS were a fragment of such a program, one might expect to see small, efficient machines built to last and to be cautious. They might use low power, precise maneuvers to conserve energy, and they might avoid loud transmissions. The quiet nature of the observed heartbeat and the minimal heat signature could be consistent with extremely efficient, careful engineering. Yet, the von Neumann idea raises questions about where the larger replicating infrastructure would be, and why we would see just one or a few of these devices. The idea is powerful, but it needs more data to be convincing. A third engineered hypothesis is that 3I/ATLAS was a specialized scout, a small, focused instrument built to map particular things like magnetic fields or planetary atmospheres. In this model, the object would keep a low profile, pinging gently, scanning its environment in narrow bands and then moving on. The scanning behavior we observe near perihelion fits this idea well. Pulses in brightness, small particle spikes, and magnetic tuning all make sense if someone is running a set of careful sweeps. A scout might also be passive much of the time, only transmitting when it needs to send data or when it finds something notable. That could explain the brief, aligned radio pulses and the later disappearance. There is another engineered idea that blends with natural material, a shell or envelope around a core. Imagine a relic object, perhaps natural in origin, that has been modified or enshrouded by an engineered skin. The skin could be reflective, designed to collect sunlight or to hide what is inside. It could produce sharp glints and act as a sail for small course changes. If 3I/ATLAS had such a surface, the cold spots might be places where equipment or sensors were tucked below the skin, insulated from heat. This hybrid idea is appealing because it explains the mixed signals. Some parts read like natural rock, others like panels. It gives us a way to understand both the irregular composition and the structured glints. Let us also consider the idea of an active sensor array, not a probe designed to land or to deliver a message, but a device built to gather data and then move on. Such a system might include LIDAR-like pulses, radar sweeps, magnetometers, and very low-power transmitters. The faint radio heartbeat could be a low-rate telemetry format, sending concise packets to something far away or to other devices. If a network of such sensors crosses a system, they might coordinate silently and efficiently. This model fits with the VA, the very subtle patterns in radio and magnetic data. There are also more speculative theories that push gently into imaginative space, yet remain rooted in physical thinking. One such view imagines a living probe, a piece of spaceborne life that evolved in the interstellar medium. It might not be alive in the way we are, but it could be a self-maintaining structure that responds to stimuli, changes its surface properties, and moves with a kind of instinct. If a living thing had evolved to harvest charged particles and light, its behavior could look engineered and natural at once. The glints could be reflective cells, the cold spots could be metabolic regions, and the heartbeat could be an electrical rhythm. This idea is harder to test and easier to imagine, and for that reason it excited a few creative minds and made others cautious. For each of these theories, we must ask a few steady questions. What energy source could the object use, and what motive might it have? Energy could come from the sun, from stored reactors, or from harvesting ambient particles. Solar sails and light pressure are surprisingly able to move objects if they are very light. Radioisotope thermoelectric generators offer long-lived power, but produce heat signatures that instruments should see. Devices that harvest ambient charged particles would be stealthy and could produce small rhythmic signatures as they cycle power. The recorded cold spots suggest some parts did not heat as expected, perhaps because they had insulation or because they used energy differently. As for motive, we can be simple and patient. The most common motives imagined were observation and mapping. A probe might be sent to gather data on planetary systems, looking for signs of life or technology. It might measure magnetic fields, which tell a lot about planetary interiors and atmospheres. It might sample radio noise to find technological signatures. It might test a world's magnetosphere to see if the planet supports a stable climate. Another motive could be reconnaissance, mapping safe routes, hazards, and resources for a later mission. Or perhaps the object was a messenger or a harvester, though the quiet behavior of 3I/ATLAS makes those motives less likely from the data we have. Now, let us take a breath and look at how each theory fits the observed oddities we recorded. The non-gravitational acceleration. Artificial probes explain this easily by using small thrusters, adjustable sails, or by changing orientation to catch sunlight. Natural outgassing also explains it, but the lack of strong gas signatures makes the probe idea cleaner in some ways. Specular glints and facets, engineered panels or membrane surfaces explain sudden, sharp glints. So do polished natural surfaces or thin ice films, but the combination of radar hints of planar reflections and glints in multiple longitudes points towards structured surfaces rather than simple natural polish. Cold spots and thermal oddities, a probe with insulated compartments or panels that reflect and protect internal equipment would produce uneven heating. For natural explanations, layered minerals or specially arranged dust could also do it, but the pattern of cold spots matching the timing of pulses nudges the belief that something active was shaping thermal behavior. Heartbeat-like radio signals, natural sources rarely produce strictly repeating narrow-band pulses aligned to a hydrogen-like frequency. A deliberate transmitter or a scanning sensor fits best. Yet a sensitive radio instrument might pick up harmonics from plasma interactions that mimic such pulses. The evidence leans toward engineered emission, especially when the pulses align with other features. Course corrections and stabilization. Tiny nudges are easy to imagine for an engineered craft. For natural bodies, it's harder unless there is uneven outgassing. The fact that simulation showed alignment with Earth's orbital plane in some private runs made a few scientists think the path seemed chosen, not random. Disappearances and sudden accelerations as it left. A probe that accelerates to avoid detection or to rendezvous with a far-off craft fits such an exit. Natural objects can pick up speed from slingshot effects, but the final angular shift recorded in some radar echoes added flavour to the probe hypothesis. After weighing these points, many scientists who saw the full set of observations quietly favoured a probe or scout model. The case was not closed. Evidence in science very rarely makes absolute proof, but the probe story stitched the clues together in a way that felt smooth and plausible. Some senior researchers described their thinking as cautious belief. They were not ready to call it proof, but they judged the artificial explanation more likely than many natural ones given the full pattern. There were also social reasons this theory gained traction. A rumoured internal draft at a well-known Search for Life lab, discussed privately by a small group of researchers, suggested that the narrow band pulses and the motion profile fit a recon probe signature. The draft was careful and hedged. It offered models and asked for more data. It was never published widely, but that quiet draft shaped conversations. Rumours of JPL simulations aligning trajectories with Earth's plane, again quietly circulated, added to the sense that some teams found the probe picture compelling. Skeptics remained, and their voices mattered. They urged better data, more repeatable observations, and careful analysis to rule out all possible natural effects. Their caution was science at its best, a steady insistence that the easiest path is often the natural one, and that extraordinary claims require extraordinary evidence. Those debates were not heated so much as hushed and intense, the kind of discussion that happens in labs under low light as people look again at figures and adjust models. Beyond the scientific, there were ethical reflections. If a probe is watching, what should we do? Some argued for non-interference. Do not try to contact or chase it, as interference could be dangerous or could change the behaviour of something intended to be passive. Others said, careful, transparent study is the only wise path. These are human questions wrapped around a cosmic event, and they show how an object in space can make us ask about our own responsibilities. There were also quieter stories of people changed by the theory. A graduate student who had spent months modelling natural outgassing admitted privately that, after seeing stacked light curves and the radio heartbeat, she found herself writing program notes with the word probe in quiet letters. She told a friend she felt like a child peeking at a new animal in the forest, part scientific duty, part wonder. A retired engineer who had spent his life designing satellites saw the cold spots and glints and said softly that if he had to design something to be efficient and quiet, it would look a lot like what the teams observed. As we sit here in the calm of this telling, consider the gentle logic the probe idea offers. It accounts for many of the anomalies without forcing too much imagination. It fits the pattern: gentle course corrections, planar reflections, faint radio pulses, efficient thermal signatures. It leaves open questions, yes, but it gives a clear frame in which those questions become research tasks, testable and kind. At the same time, keep a soft openness to natural explanations. Space surprises us. New materials, odd fractures, previously unseen coatings of ice or dust can mimic behaviour that seems designed. Electromagnetic interactions in rare plasma conditions can create repeating signals that look almost deliberate. The history of science is full of mysteries that resolved into beautiful natural processes, so the strongest stance is both thoughtful and patient. Hold a favourable hypothesis, test it everywhere you can, and be prepared, gently, to change your mind if the next observation suggests another path. Tonight, in this chapter, we have walked through the main ideas people use to explain 3I/ATLAS. We stood with natural origins and with engineered ones. We considered living probes and self-replicators, scouts and shells, radar swarms and fragment clouds. We listened to rumours and drafts that circulated privately, to simulations run in quiet rooms, and to the small human acts that kept data safe or hidden. The theory that the object was a probe, a careful autonomous scout, fits many details and captured the imagination of many who looked. It is not final proof, but it is the guiding story that moved the conversation forward. As you breathe now, let the thought settle that science advances by making best guesses and then testing them kindly and patiently. Whether 3I/ATLAS is an engineered visitor or a marvel of nature, the theories we use are tools for learning. Keep your mind open and calm, and let the work of careful observation continue to guide us. Chapter 10. The Disappearance. Why 3I/TLAS left too quietly? There is an odd kind of silence that follows something leaving. It is not empty. It is full of the small things left behind. A scraped ring in the grass, a faint scent on the wind, the way a chair faces a door that is no longer open. When 3I/ATLAS began to move away from us, the silence was similar. Not empty, but thick with questions, with small traces and unfinished records. The final act of its passage was not a dramatic blast or a clear farewell. It was quiet, efficient, and in some ways stranger than its slow approach had been. As the object crossed the inner solar system and then started its outbound arc, the first striking thing was timing. Observers expected a smooth, gravitationally driven exit. Objects under the sun's pull should leave on paths set by mass and momentum. But the last stretch of 3I/TLAS's path did not match the tidy curves in a textbook. When teams ran models backward and forward, they found that the object accelerated a little faster than predicted. It was not a roar, not a huge jump. It was a small, clean push, enough to nudge the trajectory into a slightly different lane. Radar stations that had been tracking faint echoes reported something more curious. A tiny angular shift in the echo geometry, recorded in the last frames. In other words, the way the radar reflections arrived changed for a fraction of a second. It was the sort of detail that can come from a spinning fragment or a changing surface. But the timing and the shape did not match a simple breakup. Instead, the echoes returned as if a thin plume of energy or some directed effect had altered the way radio waves scattered. For technicians who had worked with ground-based radar for decades, the pattern was unfamiliar. It was not noise. It was a brief, sharp twist in the echo geometry that then vanished. Those technical points fed into one of the most striking images of that final phase. The last clear picture taken by a wide-field instrument did not show flaming jets or a cloud of dust. It showed a faint light trail, a narrow streak that persisted for a few frames and then tapered off as the object moved beyond the instrument's reach. To those who studied propulsion, and to those who simply watched, it read like a whisper of thrust. Not a plume of vapour or dust, but something narrow and controlled, a soft tail in the dark. Combined with the radar angular shift, the image gave the quiet impression of a final adjustment, a deliberate economical push to change vector and speed. The quiet exit raised many questions. Why accelerate now? Why adjust, however slightly, as if a silent pilot were making a final correction? Some analysts proposed practical answers. Perhaps the object had been conserving energy and used a small burst of stored power to alter its path. Perhaps it had hidden devices that activated at the last moment to prevent being tracked, or to rendezvous with an unseen companion. Perhaps the push aligned the object with a corridor that minimized its exposure to the sun's particle wind. Each explanation felt technically plausible in its own way. Each also hinted at intentionality. One simulation, quietly circulated among a network of independent modelers, suggested something even more unsettling. The model took the final recorded positions and, allowing a narrow window for small impulses, projected the outbound path far into interstellar space. The resulting corridor pointed not to a random vector but toward a region of the sky, where other faint anomalies had once been reported. The model did not prove destination or intent, but it raised a small, persistent question. Did the object leave in the direction of something, rather than merely away from us? As 3I/ATLAS moved outward, its radio heartbeat faded into the noise. Instruments that had once caught the faint repeating pulses later found only scattered static. The rhythm that had seemed so meaningful during approach slowed and then stopped. For a time, that absence felt like a reply, silence as an answer. Some scientists felt it was simply a matter of the signal dropping below detection thresholds as distance increased. Others felt that the object had chosen to go quiet. The idea of a probe deciding to stop transmitting until it reached a safe distance fit the model of a cautious, efficient device. There were also small, precise events that complicated any tidy story. During one monitoring window, a magnetometer array recorded a 14-second gap in local magnetospheric noise. The instrument saw a steady background hum from the planet's magnetosphere, then a short, abrupt silence, and then the hum returned. No solar event coincided with the gap. No instrument faults explained it. Researchers debated whether the gap was related to the object's passage. Some proposed that a passing probe could, in theory, generate a local field disturbance that would quiet certain natural emissions for a moment. If the gap was connected, it would be a delicate, fascinating sign of interaction at a planetary scale. Another unsettling detail came from audio-like inspections of long-term radio buffers. A few arrays had saved continuous recordings that, when later examined, showed faint echoes that matched the timing of 3I/A, TLAS's last observed returns. These echoes were so weak that they could be dismissed as stray reflections. Yet when analysed together with the radar angular shift and the faint light trail, they formed a small constellation of coincidences that felt too ordered to be mere chance. For many, the final hour felt like a short, quiet conversation, ending in a few lingering phrases. Publicly, the narrative of departure was calm and measured. Official bulletins noted that the object had exited the inner solar system and that its motion remained unbound to the sun. They reminded the public that interstellar objects pass through on long arcs and that most do so without posing any hazard. Behind closed doors, however, some teams continued to probe the last moments with intense focus. They reprocessed frames, recalculated orbits with new parameters, and requested long-term monitoring from arrays that could still follow the object at extreme range. One of the most human responses to the quiet departure was a sense of loss. Observers who had watched the object for weeks felt a kind of grief as the signal faded. It was not grief born of fear, but of a fleeting intimacy ending. They had become invested in the pattern of pulses and glints. The slow, efficient acceleration that took the object away felt like a polite exit, a door closing softly. In emails shared among teams, some wrote small lines about returning to ordinary work and about the odd, lingering habit of checking feeds for a sign that the object had come back. And yet the quiet exit did not mean the end of the story. In the days and weeks that followed, search campaigns extended their gaze. Deep field images were taken in the outbound corridor. Long integrations scanned for faint echoes, for debris, for companions. Special teams combed through archival data to see whether anything had been missed. A faint marker in an old radio buffer, a tiny arc in an old radar file. Some found hints, a faint reflection recorded by a far-off array months earlier that matched the outbound corridor when reanalyzed. A weakened, short-lived burst in a radio archive that lined up with a predicted crossing. Each hint was small, and many proved to be false leads. but some remained stubborn, like small embers that resist being blown out. A quiet, long-term task began: cataloguing. Scientists gathered every frame, every log, every whispered note from technicians who had stayed nights to watch. The archive swelled with timestamps and raw data. Students and volunteers spent months running blind checks and independent analyses, looking for patterns and testing models. The slow work of science unfolded in patient increments. While agencies and public attention moved on to other stories, those who had seen the pattern knew that every small file might hold a key. And there were human stories that grew from the disappearance, ones that would appear later in the public record. A weather balloon over Antarctica, launched by a research team monitoring upper air conditions, was recovered and had something small attached to it. Not large or dramatic, but a microscopic fragment with isotopic ratios that did not match typical Earth materials. Analysis showed anomalies in composition that were puzzling, and though the fragment was tiny, its presence was a magnet for speculation. The idea of a stray fragment from an interstellar visitor falling into Earth's reach fed a quiet desire for physical evidence. It was a puzzle no lab could lean on alone. It required more data, more confirmation, and time. In the end, the disappearance of 3I/ATLAS left us with a calm, patient set of open questions. Did it accelerate to avoid being tracked, to rendezvous, or simply to take a more efficient path back to interstellar space? Did its final angular twist mean a deliberate change of course, or a subtle physical process we do not yet understand? Were the faint echoes, the magnetospheric gap, and the tiny Antarctic fragment all connected, or were they separate events that our minds wanted to bind into a single narrative? These questions were not urgent in the way crises are urgent. They were gentle, persistent puzzles that would guide research for years. They invited long, careful observation and the patient work of cross-checking data. They also invited humility, that sometimes the universe gives us a scene that is beautiful and clear in its own terms, but resists the neat closure our minds like to make. As you relax now, imagine the final frames: a slim streak of light, a subtle bend in a plotted curve, a heartbeat that fades. Imagine rooms around the world where teams sit quietly after midnight, replaying the last images, saving copies of files, and discussing where to search next. The disappearance was not dramatic. It was a soft closing of a door that left many of us on the porch, leaning in, listening for a sound that might not return. In the next chapters, we will trace the aftermath in detail. We will examine the small physical traces that surfaced, the paperwork and reports that emerged later, and the human choices that shaped how the story was told. We will look at what 3I/ATLAS left behind, literal and figurative, and we will consider what those clues might mean if we accept, gently and seriously, that this visitor was more than a passing rock. Chapter 11. The Unsettling. Aftermath. What did 3I/ATLAS leave behind? When something passes through a place, it almost always leaves a trace. A bird leaves feathers, a ship leaves a wake, even the faintest visitor touches the air and alters it. After 3I/ATLAS left our neighbourhood of space, people began to look for what it had left behind. The search was not loud or dramatic. It was careful, slow, and full of small, patient actions, recovering tiny fragments, scanning old recordings, rechecking instrument logs, and asking questions that were both scientific and human. What followed the object was not a single, clear gift. It was a scatter of hints, small pieces, and odd readings that together made a puzzle we could not put down. The first real physical clue came from a place far from the big telescopes and secure rooms: a weather balloon launched over Antarctica. The balloon was part of a routine study of high-altitude winds and upper-air chemistry. When the team recovered the instrument package, they found something small clinging to the payload, a particle no larger than a grain of sand. At first, the find seemed meaningless. Researchers expected dust on many recovered balloons, but when the particle was sent to a lab for analysis, it did not behave like ordinary dust. In a clean room, with white coats and soft gloves, scientists looked at the fragment under powerful microscopes. They used imaging tools that make tiny things look large and maps of composition that tell what elements are present. The fragment was strange. It had layers like a tiny onion, but the layer order and thickness did not match known micrometeorites. The isotopic ratios, the small differences in versions of elements like oxygen and carbon, did not fit Earth patterns. Those ratios are like fingerprints for where something formed and what it has been through. The lab noted that the ratio suggested a history outside our solar system, or at least a history that had not matched common bodies we know. The report used careful words: anomalous, not consistent with known terrestrial sources. In other words, the fragment surprised the experts. Because the find mattered, labs handled the sample the way we handle rare things, with rules and caution. Teams set up sterile benches, they limited who could touch the data, and they ran parallel tests in different places to avoid mistakes. Mass spectrometers read the fragment's atoms. Electron microscopes showed tiny crystalline structures that looked like small sheets folded in odd ways. Surface scans revealed traces of coatings that did not match known minerals. Some instruments showed traces of heavy metals in ratios we have rarely seen in meteorites. Other tests showed microscopic pits like drilling marks, but at a scale so small that only the most precise tools could measure them. The sample was tiny, but each test added threads to the story. Taken together, they suggested the fragment might be more than a broken piece of rock. It might have been part of a surface, or a shell, or a material treated in ways we do not use on Earth. Alongside the physical sample, engineers and analysts dug deeper into the instruments that had watched 3I/ATLS. They reran calibration files. They pulled archived radio buffers and played them at different speeds and filters. In many cases, what first looked like noise turned into structure when reviewed under different methods. Some radio arrays found echoes that had been buried under routine interference. Magnetometer teams re-examined data and found the short, strange gaps that had once seemed random. These gaps could sometimes be explained by local effects. Other times they resisted all simple accounts. The pattern was a careful weaving of weak signals that, when combined, suggested interaction with the object. One long and patient search involved the study of particles in Earth's upper atmosphere and the magnetosphere. Teams looked for tiny changes that a passing object might cause. Small waves in charged particle flows, slight changes in the balance of ions, short-lived field disturbances. A few stations reported brief anomalies, tiny shifts in particle counts that matched the timing of the object's nearest passes. Those signals were faint and could be explained in other ways, but because they lined up with other small hints, scientists saw them as part of a whole. In careful language, they called the set of anomalies a pattern of possible excitation. In other words, something outside normal background had nudged our space environment briefly. Institutions that study space weather and the near-Earth environment took the findings seriously. They opened new coordination channels, asking laboratories and observatories to share raw logs. An international team formed, one that mixed radio specialists, chemists, particle physicists, and materials scientists. The team agreed on strict methods, independent blind tests, rechecks, and protocols to rule out contamination. They worked slowly and with care. Over months they ran dozens of analyses, some showing possible matches to non-terrestrial origins, others yielding null results. Science talks like this, not in big final acts, but in a long thread of tests that add up. One thorny issue was contamination. Every lab must guard against tiny earthly contaminants that sneak into samples. Plasticizers from gloves, airborne soot, or residues from the lab itself can all change results. To avoid this, teams use clean rooms, special tools, and cross-checks with blanks, samples that should be empty. They compared their data with controls and with samples that came from deep sea cores, polar ice, and space dust collected in other missions. Some labs found that certain features of the fragment matched no known terrestrial source. Others warned that a few signals could come from long-range fallout of human activity. The debate was healthy and patient. It kept scientists careful and honest. While labs argued and retested, the public story shifted too. People wanted answers. Some news stories sought the dramatic, others were careful. Forums and online groups discussed the fragment and posted images of the sample. Citizen scientists reanalyzed open files, stacking images and looking for faint traces. That public interest brought helpful hands. Many small teams found things that larger labs might have missed. Amateur radio enthusiasts sifted through archived recordings and highlighted faint repeating tones. Backyard astronomers reprocessed time-lapse frames and found weak glints that matched professional images. The collaboration between amateurs and pros was quiet at first, then increasingly central. It showed a strength. People not in formal labs can still add to evidence with care and good method. There were also classified threads in the aftermath. Some government reports, marked up and shared only inside secure channels, mentioned external excitation in reference to local environmental disturbances. Those phrases always made public scientists uneasy. They asked for release of non-sensitive data to check findings. In many cases, agencies responded by sharing vetted data sets with cleared scientists under data sharing agreements. The balance between public science and national security became a careful dance. Each side argued their point. Scientists wanted data openness to verify claims. Agencies wanted to guard tracking methods and avoid revealing sensitive capabilities. This tug shaped how quickly some evidence reached the public. Beyond particles and fragments, some labs looked for chemical traces in biological systems. A team of biochemists tested water samples from high-altitude collection points and runoff near research stations. They sought unusual microbial forms or unexpected chemical residues. Most tests showed normal biology and chemistry. A few flagged tiny molecules that did not match common earthly patterns, but these results were weak and required more study. Scientists remained cautious. Extraordinary claims require strong proof, and the labs kept their standards high. The aftermath also changed how institutions prepared for future events. Space agencies revised data release policies and create special working groups to respond when interstellar visitors appear. Universities added new courses on handling rare samples and on international sharing for unusual space events. Funding for wide-field sky surveys increased. Private foundations supported clean lab capacity in places that didn't have it before. The practical result was positive. More eyes, more labs, and more care when something strange arrives. For many people, the real legacy of the aftermath was human. The researchers who worked late nights felt a common bond. They traded notes, they saved files, and they created shared archives meant to live beyond any single person. They wrote careful papers, then softer essays about what it felt like to hold a tiny fragment under a microscope and think it might be from somewhere else. Their writing mixed hard data with quiet wonder. They reminded the public that science is not just about quick verdicts. It is about months of careful study and about being willing to say, "We do not know yet." The little hints left behind by 3I/ATLAS never created a final proof that a probe had visited us. They also didn't shrink to nothing. Instead, they formed a slow-growing case that something uncommon had passed close enough to touch our instruments and to leave very small physical traces. Some tests leaned toward non-terrestrial signatures, others suggested caution and the need for more data. That tension is the heart of good research. It keeps people humble and keeps the work honest. If you imagine this scene, picture clean rooms with soft light, instruments hissing quietly, the slow whir of centrifuges, and scientists sitting with warm mugs as they read printouts. Picture long tables where teams spread images and notes, and under small lamps they compare lists of numbers. Imagine the patience of months where teams test and retest, share and argue, and finally publish small, sober reports. That is what the aftermath felt like. A long, careful response to a gentle mystery. As the chapter closes, know this. 3I/ATLAS did not leave behind a simple answer. It left threads that ask for time and care. It left small materials to study, weak signals to analyse, and policy shifts that make future study easier. And most of all, it left a renewed sense of curiosity. A soft, steady reminder that the universe is full of things we can learn from if we take the time to look closely and listen patiently. Chapter 12. Final question. Was 3I/ATLAS watching us, or calling something else? There is a quiet, heavy question that sits at the centre of this whole story. It is the kind of question that does not need loud words. It only needs a moment of stillness, the same stillness you feel on a clear night when a single star seems to look back. Did 3I/ATLAS come to watch us, to learn who we are and what we do? Or did it come to send a signal outward, to call something else in the dark and say, "There is life here"? Both ideas are possible. Both ideas ask us to think slowly and clearly. In the end, we have to weigh the signs we saw, the motion, the light, the radio heartbeat, the small traces left behind, and the way institutions and people reacted. Let us sit with each possibility for a long, calm moment and let the evidence speak gently. First, consider the idea that 3I/ATLAS was watching. If that were true, then many pieces of what we saw fall into place. It moved with a careful path. It made small adjustments instead of wildly tumbling. It showed patterns in brightness that looked like scans. It registered tiny effects in the magnetic and particle fields around it. It had a weak repeating radio pulse that turned up in quiet ways. Those facts read like a chart of a visitor that wanted to learn about the system it passed through. A watcher does not need to scream. It only needs to listen and to take careful notes. It wants to be small, hidden, economical. That is what many of our instruments recorded. Subtle, efficient actions that favoured quiet observation. Think about how a watcher would gather data. It would measure magnetic fields to find planets with iron cores and liquid layers. It would read radio noise to find signs of technology. It would sweep light to map surfaces. It would sample particle flows to learn about atmospheres and solar winds. The pulses we saw near perihelion match those kinds of tasks. They are the natural tools of a surveyor. The cold spots and reflective faces could be sensor arrays, or protection for delicate instruments. The faint glints might be parts that catch sunlight when a sensor rotates to look at something interesting. The very small pushes in motion might be precise adjustments to hold a steady line of sight while it scans a planet, or to keep itself in a safe corridor where it can watch without being disturbed. There are human stories that give this idea weight. People who watched the images said it felt like being looked at. The retired technician who noted shadow moves, the private satellite operator who felt a small odd interference, the amateur in Chile whose time-lapse showed repeated glints, all of them felt a kind of attention from the object. Those feelings are not scientific proof, but they point to a shared human sense. Where many people notice the same odd things, it often means something real is happening, even if we do not yet have the whole explanation. If 3I/ATLAS was watching, it would explain why some agencies reacted so quickly and quietly. A system that carries a visitor designed to observe would be worth careful study and guarded handling. Nations that maintain deep space tracking would want to know who watched us and what they learned. That does not mean conspiracy. It means that any unknown here in our neighbourhood deserves caution. But to those who later read the edited logs and the restricted data, the secrecy looked like an effort to hide. It could also have been an effort to hold scientific information long enough to be checked and understood before it went to the public. A cautious, sensible move in many ways. Now let us consider the other possibility. 3I/ATLAS was calling outward. Maybe the pulses were not meant for us at all. Maybe they were a beacon or a marker or a brief check-in to some distant network. If this is true, it changes the story. The path and actions we saw might be less about learning us and more about signalling to some other observer who waits far away. In that picture, 3I/ATLAS would be part of a larger system, a scatter of devices left across star systems and to send quiet call-outs when they find something interesting. The weak heartbeat near the hydrogen frequency would make sense as a universal marker. Hydrogen is common everywhere, and using it as a beacon frequency is a neat way to make sure many kinds of listeners, anywhere, will be able to notice. There are small facts that nudge toward the calling idea too. The direction of the final exit, when rerun in some private simulations, lined up with areas of the sky where other odd signals had been reported in the past. Those matches were not strong proof, they were hints, but hints matter. A caller might make a short pulse at a certain time, then move away quickly so it is less likely to be tracked and disturbed. A calling device might be set to transmit only for short windows to save power and to avoid drawing too much attention. If 3I/ATLAS were calling, it might be a deliberate brief shout to a network that sits far out in space. Perhaps a network that logs the locations of interesting systems, or that passes data along between nodes across long distances. If it was calling, we must ask who the listener could be. It could be other probes, other devices that drift between stars, listening for signs of life. It could be a central node in a slow, galaxy-wide mesh. Or it could be a signal to a distant origin point, the home system of the probe, waiting to hear if a mission found something worth harvesting or watching more carefully. The calling idea hints at a scale and a time sense far greater than our single lives. It suggests patient engineering and broad plans. Both ideas, watching and calling, are not mutually exclusive. A small device might do both. It might stop to look and then send a short report outward. It might scan carefully, gather a small packet of data, and then send that packet on a narrow beam to a distant listener. It might be both observer and messenger. Thinking this way changes how we feel about the tiny pulse we detected. It could be a report card, a note. We saw a world with signs of technology and life. Or it could be a simple environmental ping meant to test whether the system is inhabited. We cannot know yet. If we accept the idea that 3I/ATLAS was either watching or calling, we must face new questions that are calm but heavy. What did it see when it watched? Did it register radio noise from our broadcast bands? Did it notice the telltale signs of industrial activity, like narrowband transmissions or heat patterns? What did the faint magnetospheric gap mean? Was it a side effect of the probe's passing or an experiment by an active device? If it was calling, did its signal reach anything? Did a distant net record the ping and note our coordinates? These are hard questions that ask for patient work, not hasty answers. There are practical steps we can imagine, done gently and with care. We can comb archives and listen again, stack recordings, filter noise in new ways, and rerun old data with fresh methods. We can look for repeats of the heartbeat in other datasets that might have been missed. We can check the outbound corridor for other fragments or faint echoes. We can search for coordinated signals that might match a calling pattern. Scientists already began such work after the event. They set up longer monitoring windows on deep space arrays and agreed to share vetted data in special groups. The slow work of careful listening is the best reply we can give now. There are also moral and social questions that come with the two ideas. If we are being watched, do we change our behaviour? If a device has noticed our broadcasts and our signs of technology, are there ethical reasons to do nothing and remain quiet? Some scientists argue for caution. Do not answer aggressively. Let the observer be. Others think transparency is the best policy. Share what we know and let the world decide. These are not easy choices, and history offers no clear instruction. The best course is likely a mix of careful public discussion, prudent scientific study, and measured policy that allows facts to lead. If the object was calling something else, we might worry that our signal will reach listeners we do not understand. We might worry that drawing attention to ourselves could have unknown effects, or we might find comfort. Being part of a cosmic network would mean we are not alone, and a message sent outward might draw friendly attention. Both feelings are real and natural. The important thing is to move with care and common sense. There were human moments in the weeks after the event that showed how deeply people felt these questions. A group of school children wrote letters to a team of astronomers, asking whether the object was friendly. The astronomers answered honestly, saying they did not know. A retired engineer, who had spent nights staring at plots, wrote a short essay about his fear and hope, how both feelings lived together. Scientists in labs worked late, not because they wanted fame, but because the questions felt important and tender. That human care is an essential part of this story. One last gentle point. Even if 3I/ATLAS was a watcher or a caller, it did not arrive to judge us. It likely came as part of a program or a network with its own goals we may not share and may not fully grasp. The life of the probe would be about mapping and data, not about our self-worth. That perspective can free us from panic and bring us to clear thinking. We can study, we can listen, and we can be honest about what we do not know. As you remain here with me, let the last quiet thoughts settle in. The world is bigger than we thought, and small guests sometimes pass through it. Some come to look, some come to send a note. Whether 3I/ATLAS was watching us or calling out to something else, it left us with a calm, careful task to listen more closely, to keep our methods honest, and to learn from what travelled so far to meet our small, bright corner of the sky.